Hello, my name is Gabriel Fong, and here in this video I'll be showing you very basic baby steps of how to differentiate. So yeah, I would like to apologize. I have not uploaded anything in like I think 6 months. Yeah, I haven't uploaded any like theory-based videos in 6 months. Partly is due to because of some personal stuff that I was going through, and I couldn't find any motivation to record any videos, even though I really wanted to. Also partly because my whiteboard, the hooks that it used to be on, dropped. So yeah, I'm actually currently recording on my phone, where I normally record on my computer, but because the angle has switched a bit and I got a stand for Christmas, I can record on my phone. So alright, before I digress even more, I would like to say that this video is dedicated to Miriam. So Miriam, if you're watching this, I hope that you grasp how to do differentiation before your peers do, and if your peers want to learn how to differentiate, you can forward them this video. Okay, so to start off, we need to understand what differentiation is and its origins, which might seem a bit pointless because in Singapore's mathematical syllabus we don't really talk about these things. But to start off, differentiation is under this discipline in mathematics called calculus. And calculus delves into this thing called infinitesimal change. Forgive my spelling, infinitesimal change. So, infinitesimal basically just means infinitely small in the context of a calculus student. Infinitely small. And change is change. So, actually, yeah. So, to start off, right, the first thing that you all will be learning is called differentiation. So, differentiation. And the next thing you'll learn around the ending of your A math journey will be this thing called integration. Oops, this marker ran out of ink. You'll be learning this thing called integration. So, why do I say that you need to understand the history behind these two things? It'll be a very quick one. You need to understand that the reason why it is taught together is because both of them are inverses of each other. Differentiation and integration are like plus and minuses, times and divides. They undo each other, and therefore it's kind of pointless to learn one without learning the other. However, because differentiation is, I would say, more common sense, and honestly it is easier. As someone who has done it for like 2 years, differentiation is really a lot easier. So I think that's why it's taught first. Plus, it actually is a lot more logical to someone who wants to self-study. So yeah. But for now, you just need to understand that differentiation undoes integration, just like how integration undoes differentiation. So alright. Both of these are under calculus, and they both deal with infinitesimal change. However, what the difference between the infinitesimal change is, differentiation deals with instantaneous rate of change. Integration has many applications, but one of its major applications is adding infinitesimal rectangles. Infinitesimally infinite rectangles. It's okay, I will not lie that this is a very bad way to explain the differences between differentiation and integration. But for the sake of you right now, as someone who is currently just doing a differentiation video, all you have to really focus on is the differentiation definition. So let's get started then. So this is the English definition of differentiation. Differentiation deals with instantaneous rate of change. However, what is the mathematical definition? Okay, before I start writing the mathematical definition, I just want you to know that unless you are an IB student, or a student who is going to pursue an international baccalaureate diploma, you do not need to know what I'm about to do, and I will add timestamps to where you can skip. However, I believe that even if you are not an IB student, it will be very good for you to watch this segment to give you an idea of how the words instantaneous and rate of change are connected. So let's start with some function. A function, for your purposes, is basically just a graph that has only one output value for every input value. So let's have like a random function like this. Let's just call it y equals to fx. When you hear the words rate of change, you should be thinking of gradient. As in when you do y equals to mx plus c, this is your rate of change, your m component. So in chemistry, you do this thing called average rate of change, and you do this when you go to like JC and you start learning chemistry. But basically what average rate of change is, if I were to take like the graph at some point and the graph at another further point, I connect these 2 points and I do y equals to mx plus c. So this is of course with me having a knowledge of the x and y values here and the x and y values here. If I were to do this thing called y2 over y1, y2 minus y1 over x2 minus x1, this is called the average rate of change of like a graph from 2 points. So that is the rate of change part of differentiation settled. What about instantaneous rate of change? I want you to think about it. How can I draw a line on a point? And I don't know how you would see it, but let me enlighten you on how your differentiation formulas are all derived. So let's say I move this point a bit closer. Let's say here, and like I draw another gradient. You will realize that the closer your gradient, the closer the 2 points are to each other, the closer the approximation. Okay, sorry, let me repeat that. Okay, imagine that I have another cross here and I draw like a gradient over here, and I have a cross here and I draw its gradient over here. You realize that as I move this point closer and closer, its gradient will get closer and closer to this point. And eventually, when I have the point on itself and I draw like a line, I will have a line that is tangent to the function. And when it's tangent to the function, that's how you get instantaneous rate of change, because your gradient of the tangent is the rate of change of the graph. Okay, not the gradient of the tangent. The value of the tangent at that point. I'm sorry. The gradient of the tangent is the rate of change of the graph, but at that particular point. But since I just said as I move the x closer and closer, I will further better approximate this tangent line. However, you might ask me, but Gabriel, why I can't do that? Because I said that when you move it closer and closer, and when it eventually hits itself, you get a approximate tangent. But if you think about it, right, it's kind of nonsensical, because you're doing y2 minus y2 over x2 minus x2, and you get 0 over 0. So yeah, you can't get like the rate of change if you directly do y2 over y2 over x2 minus x2, because you get 0 over 0, which is an indeterminate form. So you might be asking, how do I get the instantaneous rate of change then? So this is called first principles of differentiation. First principles of differentiation. Okay, so essentially how it works is, let's have a point x fx on the graph. Alright, so let's have this be called x comma fx. And next we have another point on the graph called x plus h comma fx plus h. And okay, let's like draw this one here. So x plus h comma fx plus h. So if you realize this, right, the smaller I make h, the closer that the points are to each other. And if you realize this, if I let h be a very small point, a very small number, I mean, you realize that you can draw like a tangent that is a bit more accurate to the one that you actually want. So using our y2 over y1 formula, we get fx plus h minus fx over x plus h minus x, which is equal to fx plus h minus fx over h. So this is called differentiation by first principles, but we are missing out one thing. The thing that we want is for h to be a very small number. So you'll be doing this thing called a limit. So basically what a limit means is, how you interpret this is, as h tends to 0, what would the value of this tend to? And this is called differentiation by first principles, because you get 2 points that are infinitesimally close to each other but not exactly close to each other, and you take its gradient from these 2 points, and because the points aren't exactly the same, you can still force out a value. So as you can see, how you interpret this is, as h becomes becomes very small, basically goes to 0, what does this value turn out to be? And alright, that is basically the definition of differentiation. Now on to notations and baby differentiation. So notations wise, let's say I have some function y. Alright, I have some function y and I want to differentiate it. What I do is I write this thing called d dx y. So d dx, mind you, is not a fraction. It is an operation. And what are operations? Operations are similar to your plus, minus, multiply and divide. So this is not equal to this. Your d dx is an operation, it is not a fraction. It's just that coincidentally, because mathematicians are dumbos who cannot settle on non-confusing notation, it looks like a fraction. And later on in the series, you realize that there are a lot of similarities and properties that differentiation can take. They are similar to fractions, but they are not fractions. So please please remember that they are not fractions. So when I write d dx of y, how you should interpret it is, you are taking the first derivative of y. If I do it again, let's say I do d dx of the first derivative of y, this will be called the second derivative of y. If I do it like, let's say n times, so I do like d dx n times of y, this will be called the nth derivative of y. For your purposes as a secondary school student, there are only positive integer values of derivative like first, second, third, fourth, fifth, sixth. There are no such thing as fractional derivatives. However, if you go to university and you do this thing called partial derivatives, which I will not dwell into, you do fractional derivatives. So, notation wise, if I have a function of y equals to fx, when I take the first derivative of y on one side, I have to take its first derivative on the second side. It's just like how if I have x equals to 9 and I add 1 to both sides, I have to add 1 to both sides. It's the same logic as this. So notation wise, when you write d dx of y, the most basic way to write first derivative of y will be equal to dy dx. I'm going to remind you again that this is not a fraction, it's just notation convention. However, if you want to write the first derivative of fx or y, the way you will write it is with a comma in above the f and the bracket x. So this is the first derivative of y or first derivative of fx, assuming that they are the same thing. So for the second derivative, you have d2y and dx squared equals to f, now two commas, x. And I'm pretty sure that like if you have d3y, you will recognize that if I want to take the third derivative of y or fx, it will just be this. So that is very basic notation on how you write first derivatives or like your derivatives with respect to y or fx. So also to start off, right, you can realize that I write d dx. How you interpret d dx is it just means differentiate with respect to x. And I will dwell into this a bit more right now. So basic rules of differentiation. Let's say I am taking, let's say I have a function y equals to x power n, alright? And n is any number, n is a real number. Then dy dx equals to d dx of x power n will be equal to n times x, n minus 1. This is the most baby rule of differentiation, because polynomial functions are like the more of the easier functions to like see. So another rule is, let's say I have y equals to x power n plus x power m, where n and m are real numbers. Then d dx of y equals to d dx of bracket x power n plus x power m. And you realize this, your d dx operation will distribute across the bracket. So you will have d dx of x power n plus d dx of x power m. And you can do it like independently. This is like a basic rule. So you get x times n times x power n minus 1 plus m times x power n minus 1. Does that make any sense? So let's have some clear examples right now. Let's say I have y equals to x squared, d dx of y equals to dy dx equals to d dx of x squared, which is just equal to 2 times x, 2 minus 1, which is 2x. Let's say I have d dx of y, and y is equal to x cubed plus x. This will be the same as 3x squared plus 1, because I bring the power down and power minus 1. That is this basic rule. And let's say I have like d dx of x power half. It will simply be half times x power negative half. Very easy, right? Okay, now on to a bit more challenging rules. Not really challenging, it just makes sense. So if I have d dx of a y, it is equivalent to me taking out the a, then doing d dx of y. So when is this applicable? D dx of 3x is equal to 3 times d dx of x, which is just 3. I hope that makes sense to you. Just like how I mentioned that if you add two things together, you can distribute the d dx to both of them. When you minus two things, or like an unlimited amount of things, when you do d dx on y, you can distribute the d dx across all of the various terms. So keep this in mind, because you might be using this rule a lot. So yeah, that honestly concludes my first video on differentiation. I didn't really do much planning for this, but if you found it informative, you just let me know lah. I'm sorry if I seem very exasperated. It's because I haven't recorded anything in a very long time, and I'm currently sweating like a gorilla because my fan is switched off. I will continue up probably like after the New Year's. But yeah, for now, these are all the basic things that you need to understand on differentiation. So, till we meet again.